the NMR experiments, and the most usual ones, proton and carbon-13 spectra, but it will be very quick. Then I will focus on the two-dimensional correlation experiments, homonuclear correlation first, and then heteronuclear correlations. Then a few words about other nuclei, the most frequent of them being fluorine, phosphorus, or boron. And then more special experiments. I chose not to talk about nosy because it would be too long for this presentation, but I will show you a few experiments. Some of them are available in the sample changers. And then just a few slides about programming tips and reminders about the intranet or some things like this. Okay, so first of all, about proton spectra. So I won't tell you much about usual proton spectra for just checking the compound, if it's clean, if you still have solvent. So this is the most performed experiments on the sample changers. And sometimes people use the proton spectra to calculate reaction yields, for example. And in this case, we have to pay attention to the conditions for quantification. Quantification in a number can be reached for every nucleus, but usually we only use it for proton spectra because the quantification is strongly impacted with decoupling. So, for example, in usual carbon spectra are not quantitative. And we have also other NMR experiments parameters that are really important for
I don't think anybody said something.
Okay, I heard something, sorry.
Yeah. So 1 second, please switch off your microphones, everybody. Okay.
Je cherche le pointeur. Il est où le pointeur? C'est dans annoter ou c'est dans...
Oula, là tu me demandes quelque chose.
Je pense que je vais...
On voit ta souris, hein, donc ça c'est...
Ah ok, bah, je vais faire ça.
Ah oui, ça fait automatiquement pointeur.
Bon, si on voit ma souris, c'est bon. Okay, sorry. So a few NMR parameters are really important for quantitative conditions. So decoupling, I said it, but in proton spectra, we don't have decoupling. And another one is the ratio between D1. D1 is the time, relaxation time. It means the time, the waiting time between two scans. And T1 is the relaxation time of a proton in the molecule. And if you want to be in quantitative conditions, you have to respect D1 should be equal to at least 5 times the longest T1 of the protons you want to study. And other NMR parameters that are important are shims. You have to get a nice spectrum, and the signal to noise ratio. It has to be big enough for the integrals to be precise. Then for the process of the spectrum, if you want to be quantitative, it's very important to phase your spectrum and to correct the baseline so that your integrals are accurate. And if you are comparing several spectra, you can, it would be better to fix the integration region precisely and to use always the same. If you want to compare between two different molecules, for example, the starting compound and the product after your reaction, the the best way to do it is to choose one signal for each molecule and be careful to use similar signals. When I say similar, it's about the T1. You should select signals that have similar relaxation rates. So, for example, two methoxys or two aromatic protons, but that signals that would be great in the same place in the molecules. If you can't do that, because maybe signals are overlapped or something, if you want to be sure to be quantitative, you will have to ask for a T1 measurement so that you can be in quantitative conditions. The main question for quantification is to know what precision, what accuracy you are expecting. If you only need a few percent or maybe 5 or 10% precision, usually close to routine conditions would be enough. But if you want to calculate a very precise yield, you will have, it's better to ask me or Clément and to check that you can work in quantitative conditions. Okay, so it's over. Don't hesitate to ask questions. I see there is a discussion. No, it's okay.
I have a question.
You can use the chat if you need to ask questions. I will try to check it.
So Elsa, I have a question. So you said for normal measurements, so like 10%, let's say precision, conditions close to routine are sufficient.
Yeah.
So in terms of like parameters, when I'm programming my Proton NMR, so what do I need to change? Do I need to change the number of scans, or what can I simply change to be more precise?
If you have in a good enough spectra in terms of signal to noise ratio, if you want to be quantitative, usually the parameter you have to change is the D1. You can access this parameter in the same place that you change the number of scans. So it can be changed.
And what should I put D1? So is there any number you would...
If you want to be very accurate and calculate a yield, the best would be to ask us and to work on your system and measure the T1s in order to know precisely the value of that will be requested for D1. And if you just want to count how many protons you have on each site, usually routine conditions are okay.
Okay, so it's best to ask you, huh?
If you want to be really quantitative, the best way is to measure T1s.
Okay, thank you.
Next, a small word about carbon-13 detection, direct detection. So this is the second most performed experiments on routine spectrometers. We have several variants of carbon-13 detections. So just direct detection with proton decoupling, the usual carbon-13 spectra, then depth or J-mode, in which you have signal additions according to the number of protons attached to the carbon. In all these spectra, you have proton decoupling during the acquisitions, and both depth and J-mode are based on the magnetization transfer for a standard value of the coupling constants between carbon and proton. The usual values in organic compounds is about 135 Hertz. So this is the value we are working with on standard datasets. Maybe in some cases, very rare, such like alcenes, sometimes you have strange things. But normally in most molecules, it will be okay. I talk about these experiments because they are many people ask for depth or J mode, but in the tips I will give you, I would advise you not to use them. Only use direct carbon-13 detection, and then the two-dimensional experiments will be more informative and more rapid than using depth or J mode. So for it's usual one-dimensional spectra. I stopped there, and the next part will be on homonuclear proton-proton correlation spectra. The main three types of correlations are Cosy, Toxi, and nosy for small molecule of organic chemistry. So the difference is that in Cosy you look at the scalar coupling between two protons. In the Toxi, it is the scalar coupling, but it's the magnetization will spread along the spin system, and one proton will, the starting proton will couple with several protons if they are in the same spin system. So you can observe many correlation signals. So these two are, Cosy and Toxi, are scalar couplings, and dipolar couplings, so through space couplings, can be observed with nosy spectra. So just small things about Cosy spectra. So the standard Cosy is a very simple and very rapid experiments. You can perform it on most spectrometers during the day because it's only 3 minutes long, so it's very quick. For the processing, you don't need to correct the phase. You just have to correct the baseline, and in some cases you need to correct the T1 noise. It's very easy with MNOVA. You can see it in the webinars, for example, or during the training sessions. So with Cosy, you will get correlation for 3 J's of vicinal proton-proton couplings. So here, for example, the proton number 3 here will be correlated with 9 or 2, and 2 will be correlated with both 3 and with his vicinal, with the 2 protons of the carbon 2. Sorry. In some cases, a variant of the Cosy spectrum can be very useful. It's called the double quantum filtered, so DQF, double quantum filtered Cosy. It's a different pulse program, and we have a different process. Here we need to phase the spectrum, and it can be tricky sometimes, but the big interest of this is that you will erase all the uncoupled singlets. For example, big methoxy peaks will not appear in the DQF Cosy, so sometimes it's useful. And if you can see here that you will have different patterns here. So this doublet or doublets, you can see here which one is the active coupling. So this is the small one, and here you have the big one, the J coupling. So in some cases you can get more information. This experiment is much more, the duration is more important than the standard Cosy experiments. So use it if you need it, but you have to know that it's longer. Okay, so Toxi is another proton-proton correlation spectroscopy for scalar coupling, but the scalar coupling will spread over the spin system according to a delay. So in the Toxi experiment, you have to set the D9 delay, and this is a spin lock. A spin lock will be applied during this delay in the pulse sequence, and often we use we perform 2 or 3 different Cosy spectra with different D9 values to observe the spreading of the correlations along the spin systems. For the process, you have to correct the phase and the baseline. Okay. So depending on the size of your compound, you could get 26, 60 and 120 milliseconds, or you could start with 60 and go to 240, for example, if you have a bigger compound. Then for dipolar coupling, for small molecules, the more used experiment is nosy. So here you will get so different types of correlation signals. For small molecules, so usually the diagonal is phased positively, so it appears in red here, and the nosy correlation peaks will appear as negative peaks for small molecules. If you observe some positive correlation peaks, it could be nosy or dipolar coupling, but for big molecules, or chemical exchange, or spin diffusions in some cases for very big molecules. Usually we don't observe this. In some cases, like here, for example, we have a mixed phase artifact. This is a Cosy artifact for a strong coupling between the 9 and 10 here. So in this case, it's worth compare the nosy with the Cosy spectrum. And in this case, for example, we can see here we have a correlation that was not visible in Cosy, and we can see here the through space correlation between proton 3 and 1 of the proton 10. So be careful with big molecules, because as I told you before, the nosy effect, the nuclear over Roser effect, will decrease with the size of the molecule or with the field of the spectrometer, and in some range you will get no nuclear over Roser effect. Or a negative one. So if you don't know, if you have big molecules, the best way would be to compare the nosy with the rosy, because so rosy means a rotating frame over Roser effect spectroscopy. So it's another experiment that should show you dipolar couplings, so through space couplings between protons. It's based on a spin lock, so it's not the golden standard for dipolar couplings, because some artifacts can arise. So when nosy is okay in this part, for small molecules usually nosy is okay, and you will get, you will get negative correlation peaks for dipolar coupling. I don't know if there are some questions about this.
What do you define as big and small, like in terms of molecular weight, and where is the borderline?
It depends on the molecule size and also on the spectrometer field. So here, even for complex of alicins, I still had some positive NOE, so I was still in this region. You have to be careful